In example 2.62, we identified surfaces in cylindrical coordinate system. In this example, example 2.65, we will identify surfaces in spherical coordinate system. Describe the surfaces with the given spherical equations. We will start with the first one, part A, theta equal to pi over 3. Replacing pi over 3 for theta over here, we will get coordinates rho pi over 3 phi. Theta is the angle between the x-axis and r. This one. We mentioned before that you should be careful that this angle is obtained when you have a point in space, you project from this point onto the xy plane and you will get r. This is r, and the angle will be between x-axis and r, which is theta. Now, this is constant. So there's a constraint here. This cannot move clockwise or anti-clockwise or in any direction. So this is constant, which is equal to pi over 3. Now, for rho can take any value in space. So this is r and this is rho. And phi is the angle between z and rho. So don't confuse between r and rho, between theta and phi. So this is the point in space. These are just the projections. You got them after the projections from this point, from the original point you have in space, which is at this location, for example. So these values can take any value in space. Rho can be at any point in space, here or here or here or at that point, etc. Phi can take values between 0 and pi. We already mentioned this in this introduction of spherical coordinate system. Phi can take between 0 and pi, which means that you can start from a 0 angle over here and move pi over here to minus z. So you're gonna get multiple um, multiple cases where rho can move in space, anywhere in space, and with an angle between 0, which means positive z, to up to pi, which is sorry, which is, was the eraser, which goes in the negative direction. So you will obtain for all rho and phi values, when theta is equal to pi over 3, a plane that goes from positive z to negative, downward to negative z. So you will get a half a plane and not a complete plane from the other side, since we have a constraint of phi, which goes between 0 and pi. For part B, phi is equal to pi over 6. For pi over 6, you need to replace this equation, this value, in the equation we already have. So let's go, and we know that phi is our cosine z over radical x squared plus y squared plus z squared. Now, phi is given 5 pi over 6. So remove now our cosine and take the cosine of the left side. And so the cosine of pi over 6 is equal to minus radical 3 over 2. And we have this whole term on the right side. Now we square both sides to remove the radical from here and from here. Square both sides and you're gonna get z squared divided by this one without the square root. Now it's a little, rearrangement to this equation, you're gonna get something like that. And we saw this from the previous section, section 2.6. This quadratic surface is a cone. Given that these both are positive, this is negative, equal to zero. This is an equation of a cone. You can go back and check this. And since z is negative, over here you have the negative sign and the z term. Uh, the axis of this surface will be the z-axis. Now, so you have a cone on both sides, uh, but be careful. There's a constraint here. Phi is equal to 5 pi over 6. So if you go and find the angle of phi that starts from z, from the z positive direction, and you measure this angle is greater than 90 degrees. So you're gonna pass the y-axis and go downward to this location. So this is rho. This is rho over here. And since phi can only take this value, 5 pi over 6 cannot be less, there cannot be more than that. That means we're gonna get half a cone without the upper part of this cone. For part C, rho equal to 6, that's easy. We know rho. Rho is equal to x squared plus y squared plus z squared equal to 6, and this equation is a sphere, and the radius of this sphere is 6, and this sphere is centered at the origin according to this equation. Now for the last part, rho equal to sine theta sine phi. Okay, so we know y in spherical coordinates is equal to rho sine phi sine theta, and rho squared is equal to x squared plus y squared plus z squared. Now, this one is given. These two equations, we know them from the spherical coordinates equations. Now, this one is given. Let's square both sides, or excuse me, let's multiply by rho to get rho squared, so we can use these two equations. Rho times rho is rho squared, and multiplying the right side of this equation by rho, you will get rho sine theta sine phi. Okay, so now we know that rho squared equal to rho sine theta sine phi. You can compare these two equations now. Since rho sine phi sine theta now is equal to rho squared, according to this equation, we can write this one is equal to this one. Since these two are equal, by comparison, write this one, the right side of this equation equal to the right side of this equation. So we will get this one. Now, move y to the right side. We moved y to the right side, and by the method of completing the square for this term over here, we're gonna get y minus half to the power of 2. We discussed the completing square method in the previous section. Now, you will get also this equation equal to 1 over 4. And this equation is an equation of a sphere. And the center is 0, half, and 0, and the radius is 1 over 2. As the last example for this section, section 2.7, in example 2.6, we're going to choose the best coordinate system. You have multiple objects in real world, like a bowling ball, a submarine, a cone, a pipe, and a football. Now, there's no right or wrong answer. So we're gonna discuss. It depends which one. Maybe different people will choose different coordinate system, but there is a best coordinate system for your physical system. There is one, the best one, but not a right or wrong. You can use any coordinate system you want, but however, be careful. Some physical system, whenever using a particular coordinate system, will make your equations looks more and more complicated, and you don't want that. You want to solve your problem with the easiest possible way. So choose your coordinate system wisely. In each of the following situations, we determine which coordinate system is the most appropriate and describe how would you orient the coordinate axis. There could be more than one right answer, of course, we know that, for how the axis should be oriented, but we select an orientation that makes sense in the context of the problem. Let's discuss this. And again, I'm not gonna write an answer because there's no right and wrong answer. For the bowling ball, this shape is a sphere, and it makes sense to choose spherical coordinates whenever dealing with sphere. And you place your system at the center of the sphere. As for the orientation through the center, the orientation of the three axes, there's no preferred direction in sphere since we say that this is rotationally symmetric, which means if you rotate the sphere, the sphere is indistinguishable, which means that you cannot find the difference if you rotate a sphere. So there's no preferred direction. For rectangles, for cylinders, if you rotate a cylinder, you can find the difference between the initial position and the final position. For example, if you have a cylinder going in this direction, if you rotate it, you might have this cylinder going vertically, and the initial position is was horizontally. So you can realize that there's a difference whenever you rotate this. For spheres, you cannot. You just obtain a sphere. So there's no preferred direction like this case. In these cases, in these objects, since there's no rotational symmetry, there's a preferred direction in space. So it doesn't matter if we choose like this is the x, this is the y, this is the z, or maybe take the three axes in different directions as well. As for the submarine, this is a ship moving in water. So this object is moving. So first of all, I would prefer to deal with such an object in cylindrical coordinates. This object is cylindrical. And I would choose the z-axis, the path where this object is moving. Normally, whenever we're dealing with objects in sciences and engineering, we choose the z-axis, the axis that shows the direction of movement. Now, um, in some textbooks, they use the z-axis. In other textbooks, they use the x direction for the direction of propagation. I will choose the z-axis, okay, to point the direction of motion of this submarine, and cylindrical coordinates for this cylindrical uh, physical system. Now, This is for z, and since we're dealing with the cylindrical coordinates, r will be the distance, will be the measure sideways distance from the path, and theta is the angle that gives you the direction around the ship. For part C, this is a traffic cone. The best system could be, in this case, a cylindrical coordinate system. And the orientation goes through the center, like this, goes straight through the center, like we saw earlier with dealing with cones in as quadric surfaces, and we took the z axis as this axis at the origin, at the tip of the cone. For long pipe, this is obvious since this is a cylindrical system. The best system could be cylindrical coordinates, and the same thing applies for the submarine. For part B and part D are similar to each other. Now, for the football, this shape is ellipsoid. You could use various coordinate systems, but the best one I think is the Cartesian coordinates. And since you can go back and check the Cartesian coordinates for ellipsoid, and this is a simple equation, and for the axes, axes aligned with three principal axes. You can go and check the axis of the ellipsoid from the previous section. Um, and the long axis of the football, I would choose the Z, because you have the X direction from here to here, and you have the Y that measures from the center to the end point on the surface of the ellipsoid of the football. And the Z axis, I would choose the one with the longest distance between the center and the end point over here of the football. Keep in mind, please keep in mind that sometimes you don't know what is the best coordinate system. The best way is to go ahead and start solving your system. And if you realize later that the equations are becoming more and more complicated and difficult to deal with, so it's better to stop and choose a different coordinate system. That doesn't mean if you continue with your equations, solving and dealing and doing some derivations with the current coordinate system of your current coordinate system won't give you the correct answer, but it will complicate things for you. So sometimes the best way is to go ahead, try it out, see if the equations are becoming more and more complicated. Sometimes you're going to get a lot of terms in any single equation, and you don't want that. So you might stop and go and try a different coordinate system. So sometimes trial and error works, and some systems are obvious, like spheres. It's better to work with spherical coordinate systems, and cylinders is better to work with cylindrical coordinate systems. Thank you for watching, and see you in the next lecture, next section.